The positional notations we have discussed so far can also be called fixed point notations because we constrain the binary point to be constrained to a specific location in the representation. For n-bit unsigned binary representation, the binary point is fixed at the end of the number. But we could also easily create a different fixed point notation where the binary point appears somewhere in the middle of the number, or even at the beginning. We can then perform calculations on any two fixed point numbers as long as their binary points are fixed to the same location. However, fixed point numbers with different binary point locations cannot be added together in a computer without losing precision in our information. Therefore, when using fixed point notations, we are limited in the range of numbers that we can perform calculations on. To move beyond these limitations, we can create a new notation called floating point notation that allows the binary point to float around in the number depending on where additional precision is needed. Before we discuss floating point notations, though, let's take a quick tangent to discuss scientific notation. In scientific notation, you can represent very large numbers and very small numbers in a condensed format. For example, we could have a large number, such as the number of bits in a 3 terabyte hard drive, or we could have a really tiny number, like the charge of an electron in coulombs. This notation has 3 components. First, it has a sign component, which tells us whether our number is positive or negative. Second, it has an exponent that tells us how the decimal point will float around when we translate from scientific notation to positional decimal notation. The positive 13 exponent tells us to float the decimal point 13 positions to the right from the scientific notation, while the negative 19 exponent tells us to float the decimal point 19 positions to the left. Finally, the notation has a significant digits component which keeps track of the value of the number that we are representing with a certain level of precision. IEEE 754 32-bit floating point notation is the floating point notation used by most computers and is a system similar to scientific notation. The first of the 32 bits is used to represent the sign of the number, 0 for positive and 1 for negative. 8 bits are used to calculate the exponent of the notation. These 8 bits are interpreted as an 8-bit unsigned binary number, except for when the exponent bits are all zeros or all ones. These two special or denormalized cases are used to handle overflow in extremely small numbers, as we'll discuss later. Normalized components, the exponents, though, exist in the following range. To create positive and negative exponents, we subtract 127 from the exponent value represented by the 8-bit unsigned binary number. Consequently, we can represent a rather large range of exponents. The last 23 bits are used to represent the mantissa or fractional component of the representation. For the normalized exponent values 1 to 254, these bits are interpreted as 23-bit fixed point numbers where the binary point is fixed in front of the mantissa and an assumed 1 is placed in front of the binary point during interpretation of the number. In essence, the fractional component has 24 bits of precision despite using only 23 bits. Let's take a step back and look at those exceptions that we discussed earlier. When the exponent has all zeros, the number is denormalized. We assume that there is a 0 in front of the binary point, and we interpret the exponent to be negative 126 rather than negative 127 to maintain continuity with the normalized representation. To better understand this, let's look at an example. Suppose we have the number 1.1 times 2 to the negative 25th, and we divide that number by 2. We could float the binary point 1 to the right to maintain the normalized assumption of a 1 in front of the binary point. Now let's divide this new number by 2. When numbers get this small, we no longer want to float the decimal point around because we can't lower the exponent any further. So we interpret the exponent to be negative 126 and change the leading 1 to a leading 0 to compensate. Now we can continue to representing successively smaller numbers than if we kept that leading 1. When the exponent has all 1s, we are now representing very large numbers that are overflowing our representation. For these numbers, we have two cases. First, if the mantissa is all zeros, then we interpret the number to be positive infinity or negative infinity, depending on the sign bit. Second, if the mantissa is non-zero, then the representation is interpreted as being an error with the notation NaN, not a number. To conclude, let's look at one normalized example. Suppose you were asked to interpret this IEEE 754 represented number. First, break the number into its parts, sign, exponent, and mantissa. Since the leading bit is 0, it is positive. Next, interpret the value of the exponent as an 8-bit unsigned binary number, and then subtract 127 to get the power of 2. Finally, create the 24-bit fixed point notation by appending the leading 1 in front of the binary point and appending the 23-bit mantissa after the binary point. Now that we've got all the parts in place, we just interpret the number as 1/16.